Thank you all for coming tonight, and I'm quite honored to be here, to even be mentioned in the same name with Dr. Marich. We were talking earlier, he doesn't remember. I first met Dr. Marich in '86 in Vancouver when he was delivering a lecture at the Heavy Haul Conference. I was a young engineer, and believe it or not, he was a young engineer. And I listened to this guy. I couldn't believe the energy he had, the infectious laugh. And I went back to my colleagues at Southern Railway. I said, "You're not going to believe this guy from Australia. He's running 38 and 40-ton axle loads." And we were still struggling with 35, 36, 37. So I've always put Stephen on a pedestal and always admired his work and read his work. I've read many of his papers, and I'm truly honored just to be a part of this conclave tonight. My topic came about when Ravi contacted me. He asked for some ideas, and I mentioned several concepts, and he said, "I think the one on detection technology might be a good one." And I'm proud to deliver this today. I've been involved in various detection technologies. I've pioneered some, I've worked on some, I've used a lot of them, and hopefully I can give you a pretty good insight tonight on what I see from about we call it a 30,000-foot level, look down upon what's out there, what's working, what isn't, what do we learn from our various technologies that are out there. So that's sort of the roadmap tonight, where we're going. A bit of a disclaimer in that I'm not here to represent any of these vendors or any of these technologies, or I'm not out here to acknowledge that any of them work better than others. You can do your own figuring out of what you like, what you don't like. I'm out here to present to you what I can tell you, and I make no representations or claims that any of this stuff will work in your individual environment. So that's my legal disclaimer, and get that out of the way. Now, why use this technology? One reason is to comply with regulatory directives. In our country, in Canada, we have a number of directives that tell us you must use automated technology for things like rail flaw detection, and now it's automated concrete sleeper detection and inspection. Also, event recorders for locomotives are mandated. So these things are one reason you use it. And by the way, before I go any further, I better tell you, if you wonder why I'm up here in blue jeans and coat and what have you, my luggage ain't here. I've been here 3 days, but my bag's been in Sydney. I've been in these clothes for 4 or 5 days. So if you think Americans all dress sloppy like this, I want to just let you know that I should be in a suit and tie tonight, which is sitting somewhere in my suitcase. And I don't know if I mentioned, but it was involving Delta Airlines and Virgin Australia. So take your warning. And they were very nice. They said, "Well, Mr. Wolf, you can go buy clothes and we'll reimburse you." And I said, "When you're 2 meters tall, you don't walk into a store and buy clothes or size 14 shoes or what have you." So anyway, I apologize for my dress here, but at least I'm dressed, and that's good news. Further on, another reason for this technology is to ensure that we can comply with many of the regulatory directives that we do have for inspection, detection, condition monitoring, etc. They don't mandate automated inspection, but automated inspection certainly makes you comply or helps you comply in a cost-effective manner for many of these things that we have to measure on the equipment, on the track, on the infrastructure, on locomotives, etc. So that's another good reason. Here's a big one. The third bullet is to eliminate the human subjectivity that is inevitable when human beings go out there and inspect stuff. And I've watched these guys walk along in a snowstorm at 3 in the morning with a flashlight looking for side barrier clearance, okay? And, we know we're not going to get good accurate measurements, good repeatable measurements whenever we involve human beings in the inspection process. And I'll have a few more words to say about that later. To catch and prevent catastrophic failures like hot journals and high and wide loads that are shifted and dragging equipment and things, obviously that's another great use of this technology, is to stop a catastrophe from happening, landslides or rock slides, things of that nature. To help lower life cycle costs, the things that Stephen Marich kind of pioneered through asset management and learning what the wheel-rail interface can do, you can effectively achieve that much quicker and much greater when you have automated and very accurate performance measurements of your assets. Things like wheel profile optimization, increased tamping intervals, monitoring locomotives, and bogie performance. Now, the focus of this presentation, as I started putting this together for Ravi, became readily apparent I could not discuss the world of technology out there in a 1 hour, 10-minute lecture. There was just too much. So we're going to kind of break it up between tonight and tomorrow. Tomorrow I will focus more on infrastructure monitoring, track and sleepers and things like that. I'll give you a couple quick examples to whet your appetite tonight. But tonight's lecture we're going to principally talk about the wayside detection of equipment and locomotive equipment as well. So that's where we're focused on. Tomorrow we'll get into more of this material here, but tonight is kind of this and some final comments on what do we do with all the data. In addition, I want to bring you up to speed on a lot of what I call the emerging technologies that are out there. There's some very exciting stuff going on, some very intriguing stuff. Some of it may or may not pan out, I don't know, but certainly we need to be aware of what people are looking at, especially at places like Monash, where the research, the young people are bringing ideas to the table that really are good stuff, like the drone up here, which you saw one flying by when we were speaking earlier. But some of the topics are drones, certainly, UAVs, machine vision systems, ultrasound listening devices, rail deflection measurement, phased array, ultrasonic, rail flaw, a nice breakthrough there, radar, thermal imaging, et cetera. These are all great technologies that we really need to utilize to their maximum. Now, what do railroads want? When I was putting this paper together, I called a number of my colleagues on the big railroads and asked them, what are they doing with detection and monitoring technology? And I got a range of responses. But I call it the big A's that came back, the big A's. First and foremost, they all mentioned they want automated algorithms to find these defects, as well as autonomy or autonomous systems. These are the two big ones right here. They don't want to be looking at scans of things. They don't want to be looking through graphs and what have you. They want automated algorithms to do this, okay? So that's reasonable. I don't have a problem with that. And they love the autonomous systems, okay? And there's some exciting technology. We're going to talk more stuff going on right here at Monash with the instrumented revenue vehicle. That kind of automated, don't need people on it. They can roam around and pick up all kinds of data. That's where the railroads like it. They don't like manpower. They don't like granting track time to test equipment, which takes up capacity and increases safety issues. They want autonomous systems. They want automated systems foremost. They also want accuracy of the measurements and repeatability, and that's reasonable as well. They want to be able to do asset management. They want to be able to do trending, look at the wear rates on their assets, things like that. They want to have accessible databases anywhere in the world. They want to be able to wake up at 3 in the morning, look on their phone, and see what's going on. This is the kind of things that in today's world are realistic achievements. They want answers and not data. I get this all the time. Don't give me a stack of reports. Don't give me graphs. Don't give me this. I just want answers. Tell me what I need to do to fix my railroad, fix my equipment, or whatever. And that's a big theme that will come back. And obviously, it has to work in all kinds of weather, whether you're in the desert or whether you're in 4 feet of snow. The stuff has to work day in, day out, nighttime, daytime, etc. Now, on the track and infrastructure monitoring, I said we'll focus mainly on this tomorrow at our workshop. So please come back for that if you can. A few things that I will just show you here quickly on some vision systems, track deflection measurements, autonomous wagon measurements to whet your appetite. But this is all good stuff, but we're going to cover most of that tomorrow. On the autonomous data collection systems, here's a couple examples. On your left is the IRV that Monash has been pioneering, and many of these are out running around. What is it, close to 90 of them, or 80, Robbie? 80 plus right now, which is tremendous. And then in other places, people are using autonomous geometry systems to collect data, again, daily as it goes up and down the track. Not once a month, not once every 3 months, but every day, gathering that data and processing it and looking at trends and things of that nature. So a number of groups, ENSCO's involved in this. Andean Technologies in Canada is also putting out a automated or autonomous revenue car that can collect geometry data. And with these systems, though, the big question is always power. They all take power to run them. If you have lasers, it takes a lot of power, and people are using solar, they're using diesels, they're using alternators, they're using fuel cells, and that's always a problem with this equipment, though, that has to be dealt with. Another one that's caught my eye is this ballast integrity sensor. It's fairly simple. And you know, not a lot of people care about the rocks that support the roadbed. Everybody talks about rail and sleepers and things of that nature. Nobody talks about the rocks. I'm kind of a rock guy. I like to look at ballast. That's the bed, that's what holds, that's the foundation that holds the infrastructure together. This is a nifty little device. You insert it in the ballast. It can detect very small, minute movements of the ballast structure and prevent hopefully some catastrophic things from derailing trains, like a head wall failure, things of that nature. Machine visions are really, they've moved from experimental, I would say, to highly commercialized now, especially in the US and Canada. Machine vision systems, one is a system here from Georgetown Rail called Aurora. It's been out there for about eight years or more, and it's doing amazing things. Goes down the railroad at 30 or so kilometers per hour, looks at every sleeper, assesses the condition of every sleeper, every fastener, every bolt, every nut, every anchor, and gives you reports, automated reports of conditions and failure rates, et cetera. We'll talk more about this tomorrow. And then the one that I was involved with years ago is the development of a car, an autonomous car that measures vertical track deflection. And this is a very important thing, too, to understand. The foundation that supports your railroad is how much is that track structure deflecting as the wheels run down the track. Now, we don't have time to get into it, but I will tell you, geometry systems do not give you rail deflection. People think, you know, oh yeah, I get this. I got a geometry car. No, you don't. You get a space curve. This system truly measures the rail deflection, which we're going to talk more about it tomorrow. I think it's a pretty innovative tool that is now out there. Moving on, I'll mention a few things about what we're doing with locomotives. And I don't know down here in Australia if you have the mandates we do for event recorders and video recorders or not. Can anybody say, well, Philip, do they have regulatory requirements for an event recorder? We've had them for many years in the US and Canada, and I think some other countries. Germany has requirements for them. And so I'll briefly go through some of the stuff that's out there. They've come a long way in the last 30 years, but we have a requirement that any locomotive operated over 30 miles per hour must be equipped with an event recorder. It used to be an 8-channel recorder, and now we're up to close to 25 channels for any locomotive built after 08 or 09, yeah. Onboard videos have really taken off in the States. I would say 4,000, 5,000, 6,000 locomotives in the US are now equipped with onboard video. This has been going on a program for about 10 years. They're not federally mandated yet. They're still a voluntary program, but the railroads are finding great use of onboard video. And now the big change has been inward-facing cameras to look at crew performance. And as you can imagine, that's not all copacetic with the labor unions, but it's being forced day by day. So, and we've learned a lot of great things from it through some accident investigations. And then everybody's doing conditioning monitor performance. So just to give you an idea, this is an example of a derailment I worked on a couple of years ago where the train went down the track and we had a rear pusher unit. We call them DPU or DP power on the rear. And it had a camera facing backwards, and behind that train we saw the development of an incipient buckle here. And so when we were trying to understand what the next train came around and hit, we had proof here that yes, that train, a buckle did occur, and we did simulate and find a very high slack event went under that train, and it obviously caused what you see in the picture. So that's one example. One major railroad is using video as it goes down the track to monitor the adjacent track in double track territory and look for very precise misalignments in the track that might predict a buckle. With the video technology now, you can do this kind of stuff It's just amazing. So they're experimenting with that use of video. We're also measuring or monitoring passenger compartments in passenger trains, very helpful in derailment and other accident investigation. Quickly, Wabtec is one of the leaders in event recorder technology. You know, they always call these things black boxes, right? Plane goes down, where they go, well, we can't find a black box. Guess what? I ain't never seen a black box. They're all orange or gray, at least the ones in the railroad industry. But they're called black boxes. I guess it sounds sexy or something. Deutsche Werke, a German company, are moving into the States, and they've been big in Europe with a thing called the red box. A new player in the market, Central Railway Manufacturing out of Florida, is creating some very innovative products that are plug compatible with older recorders. It has 1 terabyte of crash-hardened memory that can withstand submersion for days. It can withstand 100 Gs, fire for 7 or 10 hours. I forget what the standard is. But this is quite an innovative product here. And SAIC has had a video camera system. Railhead is really come out with some high-definition cameras. Here's one on a commuter train monitoring each coach compartment for various things. And, you know, again, you want to know what's going on back there with people. If you have a crash, you want to know what people got flipped upside down, etc. This gives a good documentation. It's high definition, excellent. You can see signals working, signals at night, signal indications with the color screen here. And then Wabtec also makes a video recorder, as does General Electric, which seems to be into all things railroading now, GE. So as I said, these have been around for years. All right, so that's a quick summary of locomotive mounted stuff. Now, let's talk about some of the vehicle conditioning things that we have, vehicle monitoring. They're often called vehicle tracking systems for short. They usually are used to monitor, they started off monitoring shock and impact damage. So if you're a shipper of maybe electronics or something like that, high-value wine, for instance, and you want to know when the damage may have occurred to your shipment, these recorders can record shocks, impacts, temperature, pressures, anything to do with the lading on the vehicle. Been around for about the last 8 to 10 years, electronic-wise. Now, a couple of the people there, Amstead is one of the largest with their Ionics asset tracking system, where a shipper can track his or her shipment from origin to destination. They can monitor the temperature of it, the location, any impacts, when those impacts occurred. So if there is going to be a damage claim, they can document accurately when and where it may have happened. Latlon has another device out, and then Wytronics has also a WIPU asset monitoring system as well. So these are 3 of the bigger providers of this technology. Now, drones. You saw the drone earlier that Monash is using to inspect tunnels. That was what you saw up there. This is a real breakthrough technology, and it's really come about in the last 2 or 3 years, where it's really, let's say, hit the streets. And more railroads are experimenting, and every day you hear somebody using them for something different. And this is going to really change a lot of the way we inspect infrastructure, how we inspect track, et cetera. So just some of the reasons, or some of the uses are, of course, track and infrastructure and switch inspection. They're getting widespread use for bridges, especially high aerial structures where it's very difficult to put a man or person out there hanging on a rope or a snorkel or something. Very dangerous stuff to inspect bridges. These drones can go right up to a bolt, a nut, a rivet, and get a good assessment. Pier inspection for bridge piers, culverts, tunnels, antennas. Here's a big one that we want to start using them for, is special inspections that are mandated. And I found out by looking at your RISB standards, I'll show you next slide, you have mandated inspections in Australia after any special event, like a storm, an earthquake, et cetera. We have the same thing in the North American environment. Before any train runs, you must have an inspection. Well, if it happens at 3 in the morning, finding an inspector to get in a truck, to drive to the office, to get the dispatcher, to get the track time, you know, that could take 3 or 4 hours right there. And then you got to tie up that section of track while a high rail truck goes down there looking. Very cost ineffective. But a drone could be launched immediately, go ahead of the next train, survey for any flooding, any washouts, any slides, things of that nature. BNSF is the leader, one of the largest railroads in the U.S. They're only one of 3 companies of all the industries that have been selected by our Aviation Administration to participate in what's called the Pathfinder program to implement drone technology into the rail industry. They have been successful. I'll note it here. They have permission to fly beyond line of sight, which is a big thing. And recently they made a 135-mile inspection trip down in New Mexico of the right-of-way with a drone. That's huge, 135 miles. So big stuff there. They're using it for snow inspection after heavy snows. And they say that they want to be able to detect rail separations as small as a 1/4 inch. If the rail contracts, you know, our northern borders are not like Melbourne. We get very cold, 30 below, even Celsius up there, and the rail can contract and called pull apart. And they want to use this to inspect rail at a detailed level, to look for any separations in the rail that a signal system may not pick up or may not find. So good stuff there for BNSF. But here's this issue. There's 3 big benefits, I think. Speed is one, as I said, to quickly get eyes in the sky out after a storm event. It's much faster than getting employees. Here's our regulation. Here's the AS 7635B1 regulation. And many other countries have similar requirements to inspect after big events like earthquake, storm, etc. So that's one use, I think. Safety. You can put a drone in locations that are unsafe or dangerous for humans, on bridges, as I said, on rock formations, in snow and avalanche areas, floods, culverts, tunnels, enclosed spaces. Very much safer than putting a person out there to try to do this stuff. And then finally, economics. You can reduce your labor and energy costs tremendously and improve worker safety. Drones come in 2 flavors. There's the fixed wing type, and then there's the rotor type. They all have their pluses and minuses and benefits. For the big flight that BN did, they used one of these fixed wing aircraft. But, you know, there's all kinds of flavors and styles. Okay, other things drones can do is do LiDAR mapping to get contour plotting of the right-of-way. Here's an example of a drone finding a slide area, a clogged up culvert right here, ballast conditions here, etc. And you end up with 3D mapping of the surfaces, which you can do with drones much quicker than an actual survey. Here's some, give you an idea of a bridge. This is a high aerial structure over a major river. Up here in the high rail truck, the guy wanted to see this connection pin right down here. But you can see the level of detail that drone can come in and zoom in on that pin construction there, or pier supports, pillow blocks, etc., splice plates, things of that nature. Pretty amazing stuff. And I don't know how many of you in the world, in this room at least, would want to get out of that truck and have to climb down there and look at it. It ain't me, I'll tell you that. All right, now, let's move into Wayside devices. There's 2 big buckets here that I've kind of broken it into. One I call legacy systems. These are things we've had around going back, some of them 50 years, okay? But they've been tried and true. We all know about them. And then at the bottom, I got some new and emerging technologies that I really want to kind of zoom in on with you. Some of the machine vision systems and things like that. So let's start moving. Before we had automated detection, most everything was, again, manual in nature, labor intensive. And as I've told you earlier, you know, what's the odds this guy out here with the sun in his eyes looking up at the undercarriage of the vehicle is going to catch a crack, a flaw, missing cotter pin or something like that? Humans being what they are, you know, it's just human nature that you may not catch everything. So we had risk here. Human bias is also prevalent in making assessments. I could walk track and count sleepers, come up with one number. Ravi might do it and come up with a number completely different based on his experience level and what he thinks, etc. So as humans, we all have those internal biases. And also as humans, everybody in this room fits what's called the bell curve, right? It's like this. That's what humans fit under. Meaning over here, you've got your A+ people. You got your B+, you got your C's, the average in the middle, then you got your bad performers on the tail end. That's the way every human population falls into pretty much, except this group. We're all the A-plussers, I can tell. You look, all A-plussers over here. But no, in reality, you know what I'm talking about with dealing with the inevitable changes in human beings. Also, you get issues of the human itself. Somebody's sick today, they've got a cold, a headache, they're impaired, they've been drinking last night, late in the hour, late into the morning, things like that, which could influence their inspection capabilities the next day. Then you have environmental influences with humans, darkness, rain, snow, sunlight, the distance you are from an object, like this fellow driving past in a truck here, is he going to see the wedge rise on that bogey like he should? And then the final bullet is something I just can't believe. I call it measurement errors. People making errors measuring things. For instance, here's an example of a fellow string-lining a curve. Many of you have string-lined a curve, right? Okay? I taught a class to a group of young railway people for a railway that was trying to give some introductory lessons to people coming in the workforce. There's some real changes in the U.S. with a lot of people retiring, what's called the post-war baby boomers. I don't know if you use that phrase in Australia, baby boomers after the war. I'm one of them. We're all retiring. We're getting old and gray and decrepit. And so all these young people entering the workforce. And they wanted me to help train some of their field people in both bogey inspection as well as track inspection. So I went up. I was shocked how many people got down and could not read a ruler. I swear to God. I'd say, okay, what's the offset of the ordinate? And the guy would be struggling, and I didn't want to embarrass him, but they couldn't deal with inches and fractions of an inch. They cannot use analog devices. Oh, they can all bring this out and go, yeah, boom, 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 boom. But reading rulers, and then I taught a class, it was about 6 years ago, on using wheel gauges. I showed how all the gauges work, all the parameters, the flange height, the flange thickness, etc. We went through it in the classroom. We had the gauges. Then I had 6 wheel sets on a trailer out back. For their final exam, they were given a gauge, and they had to measure all the parameters. You would not believe the errors that occurred just after I taught them how to do it. And I'm not talking about, one guy said it's 1 3/16, or, you know, no, it was, one guy had 1 3/16, the other guy had 2 3/16. It was that bad. And I'm not here to denigrate young people. They're great, they're innovative, but I'm just warning you, today's young people are not used to old school analog instruments. And that's another reason why automation, I think, is a great thing. Now, when we get to wayside detection, we have three big systems here. We have performance detection. You've got them in Australia. You pioneered them down here, the WILD system, the wheel impact load systems, TPDs. These are all called performance. We're measuring the performance of a wagon. Then we have condition monitoring, where we're measuring stuff on the wagon. We're measuring the thickness of a brake pad or the wedge rise or some condition. And then we also have machine vision systems that we use to often facilitate these condition measurements, and it all goes in a big database somewhere here, and we'll say a few more words about that, where it all goes. To give you an idea, just, and I got an Australian slide too, I'm not prejudicial here, but in the States we have well over 300 detectors deployed now across our networks, ranging from truck performance, WILD systems, hotbox systems, T-bogey systems. It's probably closer to 350, but it's somewhere in that range, and it's geographically, see, Canada has a bunch, Mexico has a bunch, US has a bunch, and it's all tied together in a network called ITERIS. This is a year or two old, but we were getting incoming data, almost 500 million records a month on our wayside detector systems. That's huge data storage requirements. We're putting out about 1,500 or so, 1,600 daily notification messages of a critical event. Stop the train, fix this, get this taken care of, etc. That's pretty amazing, 1,600 a day. We're looking at about 1.7 million vehicles, though, operating over somewhere around 150,000 miles of track. So it is a big system, a big network. But those are big numbers, folks, of what we're doing with detectors already. Wayside detectors really took off around 03 and 01. These are the WILD installations climbing up to, we now got probably close to 200 of them. These are the truck performance detectors that started in the early 2000s. And these are the installations of truck hunting detectors, which is kind of a newer technology coming up as well. Australia, I looked, and you have also big networks of detectors, as many of them were pioneered down here in Australia. And so this is the ARTC network showing the number of various detectors that you have. So just about every country in the world is embracing this technology. It's becoming old school, but it's good stuff. It's preventing many, many accidents. This is the investment in technology as of '08. That's the last number I could see. In my research, we were about up to $80 or $90 million US dollars of investment and about 350 to 400 total automated systems installed, just to give you an idea. The savings come about in three big buckets. This is from a study done at U of Illinois. Obviously reduced derailments, reduced labor costs, and reduced in-service failures, okay? You add them all up in those three buckets, you get close to $100 million a year in savings. So if we've invested 100 to 150 million in these detectors and we're saving 100 million a year, I'd say it's a very good economic payback for what we've invested, no doubt. All right, some of the technology we'll finish up with here is hotbox detection. Has been around for many years. It started in the 1950s. We have both standalone and integrated systems. Typically in North America, we space them at 15 to 20 miles apart. What's that, 10 to 15 kilometers, I think. We have over 6,000 installed. The problem with hotbox detectors, it catches a bearing when it's ready to burn off, okay? It's kind of crazy in a way. I mean, how many of you that fly home tomorrow or whenever, you get on the airplane and you find out that they're going to let the engine go to failure? Then they'll fix it. Think what we do in the rail industry. We ain't going to change that bearing until it's flaming, okay? Then we'll put somebody on it. But when you use hotbox detector and infrared technology, your chances of finding that bearing, yeah, you might, but you have to consider this fact right here. Bearings can heat from nominally cool to thermal runaway in less than 2 minutes. I've seen it myself on a lot of derailment studies where we've had detector readings. I've got a big derailment now in Tennessee. It went through 7 prior detectors, cool as a cucumber. And then within 7 miles of the last detector, it burnt off, huge derailment, fire explosion, etc. And you just kick, you know, why? Why didn't we catch this? Well, this is why. And this is why this system is not the best. Now, how do we get around that? Some of the cutting edge technology is using acoustics. And I want to show you a guy that's got an ultrasound system, kind of innovative stuff, I think, to use listening devices to try to find incipient bearing failures before they're on fire. Maybe give you a couple weeks to get it changed out, which I think is a good proactive way to go. Another big breakthrough has been temperature trending that was developed on the Union Pacific Railway to look at the bearing temperature over, every time it goes through a detector. And we found that most bearings start failing with slow temperature rise like this, and then they go to thermal runaway like that. So if you can catch that incipient temperature rise, you have a good chance of finding that bearing and getting it fixed before catastrophe strikes. And that's been a big breakthrough that most railroads are now doing this temperature trending from their network of detectors. Here's a typical example. We got this one stopped just in time, but another 500 feet and this could have been an explosion, okay? This is an extremely lucky one to catch it there. Overall, we've had great success in bringing down derailments due to journal bearing failures from 30 to 40 a year. In 2016, we're down close to 8 or 9 in single digits. That's a huge, huge win for our industry, especially moving crude oil now. And you've probably heard of some of the big catastrophes we've had in the U.S. with crude oil movements, blow-ups and things. This is a great news here, this graph. So we're proud that we've, between the temperature trending, the acoustic detection, greater hotbox or smaller hotbox spacing between the detectors, we really are getting the numbers down. We've got about 6,000 detectors across the U.S. network now, and they're all doing their job every day. Progress is a big one. Pegasus by Mermex System has a system. SoftRail, formerly the Signal Computer Consultants, have a detector system. Schenck from Germany has a detector system, etc. Just to give you a few names that are some of the prominent players out there. So if you're not using hotbox detectors, look into that. Now, draggers or dragging equipment detectors have been around for many years also to detect things like dragging chains, brake beam that is down, dragging across the track to get the train stopped again before catastrophic failures. Most of them use a large steel paddle. I've seen a number of rail systems, maybe short lines, and some foreign railroads I've worked with in South America that use a simple conducting rod, a copper or brass rod laid across the sleeper and wired into the signal circuit. So if a wheel strikes it and breaks it, it's just about less than a millimeter in diameter. It's very cost effective, you know, for a few dollars system. And high and wide detectors are using lasers now. And we often place these close to tunnels, bridges, adjacent structures, et cetera, where we have high risk areas. Here's a couple of the vendors of this stuff. At the top here, we have Voestalpine from Europe, and this is Progress Rail from the US. They both make a paddle type dragging equipment detector. We have thousands of these installed across North America. Now, the old granddaddy, the wheel impact load detector that Mr. Marich, I think, had something to do with years and years ago when he was a young man, and the technology progressed to the US, and these are now everywhere. We've got wild detectors. And we've greatly lowered our number of wheel failures and or rail failures by the advent of these things. We now have a rule in our interchange rule book that allows removal for any impact above 90 kips. I can tell you in reality, because of the wheel shortage and labor shortage, we don't necessarily change a wheel at 90 kips. Many railroads are up around the 120 kip level is where they'll change one out. But 90 is our standard. We can change it and bill the car owner for it at that level. Also, this is a bit of a controversy, and I always like to bring you controversy. But the shippers and the railroads don't agree on these wild detectors. And here's a perfect example. In our country, and just like here, you've got people who lease wagons and things, and we have the same thing. In fact, more wagons in the US are lessor owned or privately owned now that are owned by railway systems. And so you own a railway. You're the Marich Railway, American Northwestern. How's that? Okay. So the American Northwestern has a grain hopper. He puts it in a blowed out facility, and somebody leaves the handbrake wheel on. And you pull that car out, and you slide the wheel, and you flat spot it. It goes down the railroad, and it hits one of Mr. Marich's detectors. Kaboom, 100 kips or whatever. That wheel can now be changed out, and that poor owner, Mr. Marich, has to pay for that wheel, but he had nothing to do with causing that flat spot. That was a crew failure problem. Okay? So that's the controversy of these wheel impact load detectors and some of the politics behind them right now. We have a bunch of them out there. They're all over the place in Canada and Mexico. Foster, which bought the Salient Systems, is the premier supplier in the US. They have the most installations. They're everywhere, several hundred certainly. And they now are part of LB Foster. But it's a strain gauge installation over about 50 feet of track, 16 meters roughly. You put a series of strain gauges to capture the whole wheel circumference as it comes through to provide your alerting. Strain Stall, I think English company has a system as well. Schenck from Germany has a wheel impact load detector. And down here, Trek IQ and Vipac, which are now Wabtec, pioneered a system. I think it's the old Technis technology of strain gauge plus accelerometer to also detect wheel flats out of rounds, etc. Anybody here from Vipac or Trek IQ tonight? I'm just curious if you're now called Wabtec or you keeping the name. Does anybody know if they're still go by the name of Vipac, or are they all assimilated into Wabtec now? Anybody know? Okay, doesn't matter. And then here's another one. Vortok, known more for the Pandrel clips and things like that, has a technology group that's pioneered something called the multi-sensor. We'll talk about that a little later. but it's simply inserted into a drilled hole in the web of the rail, and it measures strain and temperature, et cetera. But they're using it in what's called the wheel check system that they bought the rights from Delta Rail, which is another form of wheel impact load detection. So it's another system out there with not exactly the old strain gauges on the web and base of the rail, but using this multi-sensor tool inside. Now, truck performance detectors are a lot different, and they measure curving performance of a wagon. How much force does that wheel put out as it goes around a instrumented curve? And I was involved in helping to put the first one in up in British Columbia on the BC Rail in '95. We subsequently put one in on the Quebec Cartier Mining Iron Ore Company up in Canada. But these things have caught on then and moved forward, where you basically are using them to catch what are called the bad actors. Uses strain gauge technology to detect curving performance. It measures both the lateral and vertical wheel set forces instantaneously. So you get the lateral force, you get the L over V ratios, you get truck side L over V, et cetera. So it's a very good device to measure curving performance and find bogies that are not performing, because if they're not performing, there's two things that are occurring. Either a derailment risk from spreading gauge, or if you're lucky, it's just wearing your wheels out quicker, and now you've got a big cost of wheel replacement. A new technology called T-bogey is using laser-based devices to measure wheel set angles of attack. I'll show you that in a minute. The problem with this system of curving performance is it's highly dependent on things like the wheel rail friction coefficient at the time you measure. It's dependent on the wheel and rail profiles of the wheels coming through, somewhat dependent on speed. So there's a lot of variabilities where a car may signal to be a bad actor in this curve, and then 80 kilometers down the track, it's behaving well. And that's just a problem with curve performance. It changes with these environmental conditions. And you can use Rule 46, it's one of our interchange rules, to alert the owner if you're producing gauge spreading forces over certain thresholds. We probably got a few more than this, but probably 15 to 20 TPDs in America. One of the larger companies is called Progressive Rail Technology. Typically, you instrument a reversing curve where you check curving performance in both regimes, left hand, right hand, and then in the middle, you look for trucks that have stayed misaligned. And you can find things like mismatched frames, twisted car bodies, certainly wedge rise is an issue with curving, broken suspension springs, and tight side bearings is another one. So it gives you an alert that something's on that car. You still may have to send a person out there with the flashlight in the rain to find it, but at least you know that car is not doing what it's supposed to do. Here's a T-bogey system from a group in Canada called Wayside Inspection Devices, Danny Du. And a lot of people like this system. It doesn't involve strain gauging. It's much quicker and simpler to put in, more cost-effective perhaps. But it measures the wheel set angles of attack, wheel set misalignments, et cetera. So here's a chart of the various parameters it will measure: angle of attack, offset tracking position, interaxle misalignments, tracking errors between wheel sets, warp misalignments, and lateral shift of the entire bogie. And if you put in 3 heads, called the HD system, you can pick up hunting instability. And several railroads think this is the way to go in terms of curving performance. This is what the T-bogey looks like. It's a standalone box with laser sensors. As you see here, this is a system called the HD for hunting detector. You need 3 boxes to pick up hunting, and tab a car for that behavior. Now, I just want to bring to you this is the way detection technology goes. You got something out there that's doing what it's supposed to do, and somebody says, hey, we can do other stuff with that same technology. And one railroad said, they went to T-bogey and said, well, you're measuring this wheel plate. Do you think you can find shattered rim defects with it? Because if they're scanning that rim of the wheel, and sure enough, T-bogey said, we can do that. And so here's an example. What they do, they scan across the rim, and looking dimensionally, they use that data to look for offsets, angles, tracking errors, et cetera. But then they say, well, if that rim is missing, we're going to pick that up too. And so here's a shattered rim example that T-bogey said, hey, there's something missing in our scan. And These shattered rims have really been a problem up in the U.S. I don't know if Australia is having the same problem. You're not with shattered rims? Oh, they're killing us. They're killing us in the U.S. It's really been problematic. Here's another use. We have wheels that have been cast in the U.S. called Southern wheels. They were made at a foundry in Alabama called the Calera Foundry. And back in the 90s, somebody was asleep at the switch, I don't know what, but there's a bunch of bad wheels out there called Southern wheels. And the AAR has mandated if you find a Southern cast wheel, remove it immediately. They have extremely high failure rates because of the casting process. They used a combination mold with some with sand and some with graphite. Yeah, graphite. So they had a split mold for the wheels. These are wheels that are cast wheels, and they had cooling problems, which led to hydrogen embrittlement and a very high failure rate of the wheels. And with the same technology, they went to T-Bogey and said, hey, the rim of the Southern wheel looks different than every other wheel we know about. Can you detect those? And boom, T-Bogey got to work, and within a week or so said, yeah, we can do that. And you can see here that here's the rim of a typical wheel, and the Southern wheel has the red trace here, and they can spot those and identify those Southern wheels, get them changed out immediately. So it's another great way that people, once they see a technology, they say, hey, what else can it do? And that's why we need young people. They're always questioning and thinking out of the box. Truck hunting detectors have been around since the 90s. Typically, they're strain gauge systems. They're measuring this back and forth motion of the wheel set, which is very problematic on empty cars, as most of you know, especially with long tangent track and very dry conditions. Does that exist anywhere in Australia? Long tangent track, extremely dry conditions. Yeah, just about everywhere, doesn't it? So hunting on empty cars is a problem, and we have detectors now, and we have rules to flag a car if we get a hunting index over 0.5. And so Salient, again, is the leader in most of these systems that detects the lateral offset or oscillatory motion, sinusoidal motion of a wheel set, and flags that car. WID, as I just mentioned, with their HD system, can do the same thing. Here's an installation, I think, that might be in Australia, actually, to find hunting instability. And Progressive also uses a proximity sensor to do the same thing. Okay, we're getting close to the end here. Automated wheel inspection. Let me get the bullets up quick. Right there. Automated wheel inspection was introduced in the late 90s to scan wheels automatically as they go down the track at track speed, to look up with lasers, shoot a picture of every wheel, characterize its shape, measure its shape, check it for condition against standards, etc. They can measure up to 80 miles an hour. They can also check back-to-back distance. The newer systems look at the wheel surface. Benavision has a system called TreadView, I'll talk about here momentarily, that can check the surface of the wheel for spalls and shells and things. And we also have a family or a couple different products called handheld devices that can also measure wheel profiles extremely accurately to the couple mil or thousandths of an inch. We have a number of wheel profile systems. This chart is a few years out of date. I know there's several others on the East Coast now. All the major railroads have at least 1 or 2 or 3 wheel profile sites. The one problem holding back wheel profile detection is the regulatory agency is still requiring a manual measurement to flag a wheel. So you can detect them with this device, but we still got to send the person out with the flashlight in the rain in the middle of the night to make sure it does fall in the defect category using a hand gauge. So that's why some railroads are pushing back, saying, you know, this is great, but we still got to put a guy out there, a girl out there at night and do this stuff. But we got about a dozen of them around, and they're doing great things with them. I think the leader in installations is the Benavision, and if you don't know, they were recently bought a few weeks ago by Trimble Company, which should be a good thing for helping them expand even further, but they're in just about every country. I've watched Vision grow from 2 employees about 12 years ago to about 90 or 80 employees today. It's been a tremendous success story, and I know they have a subsidiary here in Australia doing great things. But you can get with the system. Oh, by the way, Camby's, the president told me they're measuring over 50,000 wheel sets a day now around the world and getting data sent in on servers, and that's huge. That's a pretty big number. But you get all your traditional measurements here. They operate at low speeds, high speeds. When we first worked with this technology, snow was a problem, heavy rains were a problem, but we have overcome all those. The systems have heaters in them. They have windshield wipers to keep the lasers clean, so they work in just about any predicament now. KLD is also a big player in this thing with their wheel scan system, does basically the same thing. And we have Mermac, which is, well, it used to be called Reeves Technology, then Mermac bought it. It's been through a couple evolutions, and I think it's still Mermac. But they also have a system, whoops, excuse me. And on the portable side, for handheld measurements, still the leader far and away is Greenwood Engineering with the Mini-Prof. I don't know how many hundreds of those are around the world now. And then Vision developed a laser non-contacting system about 10 years ago that can also be used to quickly do a manual measurement if necessary. Calipri is another interesting development on the horizon. They have a system. I saw it at Intertrans a few years ago, and it kind of wowed me. I've since thought more about it, and I think there's some limitations. You got to be careful, but you can walk up like a gun and just shoot it, boom. With the other systems, you got to put stuff on the wheel, and you got to move stuff around. This you can walk up, kaboom, shoot it. It also measures rail, so for one deal you get rail and wheels, but you know, it has some limitations. But it looks really cool. Hot and cold wheel detection. These have been around for a while, used to check the integrity of the brake system. Let's see, I think maybe it comes later. On a typical train, you've got a fairly high percentage of wheels that are not doing braking. They're there, the brakes are on, but they're not producing the required force, and therefore the heat in the wheel is different. This is what these detectors find, are non-functioning brakes or sticking brakes, like at the bottom of a grade. When you've made your brake release, is a good place to put one of these to make sure all the brakes are releasing. And then on the grade, it's good to see that all the brakes are performing to standard as well. So we can use it for application and release. Or we can find things like handbrakes set on, faulty brake valves, faulty empty load sensors, etc. Mermac has one, NEM Solutions, Progressive has a system as well. Now, brings us to the emerging technologies, and largely these fall into machine vision systems that look and sound systems that listen. Pretty cool stuff here. Things that can listen to the vehicles and the bogies, and things that can scan them with machine eyes, x-rays and things like that. A couple of the big things we're looking at are these right here. Wedge rise, brake shoe thickness, okay? Coupler securement, and a real exciting one is checking all what we call safety appliances, the ladders, the handholds, the stirrups, the steps, the things that crewmen interact with, and if they're not there and they go to step down in the middle of the night and that stirrup's bent or broken, they could end up on their head with a serious injury. And so we now have machine vision. As a wagon goes by at 30 miles an hour, it can look at every ladder, every rivet on it, every bolt, you know, et cetera, et cetera. And as I said, acoustics and listening is another one. On wedge rise, there's a couple systems here. And I got a big star here. I'll get to that in a second for this. But you can measure friction casting wedge rise. It was only until in 2007, 10 years ago now, we finally got a standard for friction casting rise. Everybody in the industry knew that when friction casting rise reached a level, the truck was going to really start to degrade in terms of curving. But the owners pushed back at it and said, well, we're not going to change wedges out, blah, blah, blah. And it was a big political battle. Finally, in 2007, a standard came out for wedge rise. But it was very tedious to measure it. People didn't understand how to measure it. But now with these automated systems, we can get the friction casting rise. And It's not yet AR certified, meaning you can't condemn a car. You still must check with the old gauge, but again, we can find the cars and limit the amount of searches that a human has to do and tell them exactly what bogey to go to on which side of the car, etc. Now this star here, what's this about? I believe that when somebody gets going on this, that when you combine truck performance data, so when you tab a car as a bad actor, if you include the wheel profile data and the wedge rise data, you can pretty well narrow down what's causing that bad actor performance. Because two things that influence curving is lack of wheel set steering, hollow worn wheels, okay, and trucks with excessive wedge rise that go into a warp mode, they don't remain square, they don't curve worth a darn. And so if you know those parameters of wedge rise and wheel profile, and those are okay through your other detectors, you pretty well can narrow it down to something like a side bearing setup height or something like that. So I think with integrating these various detectors and using data mining, you'll be able to really zoom your maintenance in so you're getting, again, answers and not data. Okay. Again, leading the pack is Benavision with something called Truck View, which looks at all the parameters on the truck here. They look at the wedges and calculate wedge rise above top of bolster. They look at the bearing end cap bolts. They're looking at coupler securement. They're looking at hatches and doors. So everything up here can be measured by these various detectors as it goes by at 30 or 40 kilometers per hour. KLD, not far behind, they have something called Truck Scan. Here's an example of looking at the spring height and the wedge rise. They do the same thing here, friction casting rise above bolster. And you can see on most wagons, it's hard to look at the wedge. It's hard to see in there, and that's why it doesn't get detected all the time. Here's an example of the truck scan system picking up a broken spring by comparing the spring height of the left side of the car to the right side of the car, which ought to be nominally equal. They can see if there's a broken spring, and sure enough, their machine vision technology was smart enough to pick up the broken spring in that car. And here's how you look at various heights between the left side and the right side, and you can see one set of springs is down lower. So that's what our machine vision can do. With machine vision, we can also look at brake disc or pads. KLD has one called the brake scan system. And again, Benavision has a brake view, which looks at the thickness of the brake shoe here, or I didn't mention it, but KLD here can look at also the rotors as well on disc brakes. All good stuff again for safety appliances and finding defects. Mermec has a system as well. Coupler securement is another thing that's bit us pretty hard in North America with bolts falling out of, especially on what are called F-pin couplers. The securement plate underneath, the bolts get sheared off, and the plate falls down, the pin falls out, and as you go up the hill and the slack runs out, you pull the whole coupler out of the yoke, and you got a big mess, obviously. And we've had a number of very big derailments because of this. And also cross-key failures on cross-key type couplers, F-type, E-type couplers. As I said, it's caused several major derailments. It's very difficult to inspect manually unless you're up and underneath the car, almost impossible even with a bright flashlight. But you're looking for things like this, this cotter here in the cross key and the keeper. The systems can find those. Here's the undercarriage view, like the coupler view system from Bena, looking at these bolts. Find some missing or sheared bolts here. It's indicative that that thing's about to fail and we're about to lose the whole coupler. I can't tell you, one railroad, I heard the anecdote. One of the, I won't name the company just to keep it all fair, but he went into the railroad, tell him about this thing. He said, "We don't have a problem with that." And he goes, "Well, sir, we just stopped one of your trains yesterday. It was missing all the pins under the wear plate down there." The guy goes, "Really?" Kind of made a convincer of him. And also they can look at, on E-couplers, the cross key, the cotter pins are critical. Once that cotter breaks off or something, or is not fully wedged open, and you lose that cotter, this pin can pop out with road impacts, and then the coupler cross key can come out. I've had the misfortune of going to a huge benzene derailment where we found the last car in the train upright with the cross key just hanging out by a thread, and the whole coupler had been pulled out of the car, and the cross key was still in the yoke assembly. So it's, believe it or not, maybe you don't have that problem here, but we're having some issues there. I mentioned safety appliance inspections, obviously to prevent injuries to crewmen, making sure our handholds, our ladders, our stirrups are all in position. Very important there. And a number of vendors have devices. Bina, again, has a thing called Train View, which looks at both sides of the train as it goes by, looking at the lading, looking at the appliances, looking at doors, looking at, here's where they found a valve open on a tank car, the cap missing, things like that, just amazing. And another area they're using this for is border, at the border patrols, both on Canada border and the Mexican border, looking for vagabonds that are trying to hitch a ride in one way or another. They can find humans now with this technology, and the, what do we call it, the US TSA is very interested in this stuff for border patrol activity. So, all good stuff there. That's another view of appliance view, but shows you what it's looking for. Here's a bent ladder right in here. Picked that up and prevented a crewman maybe from reaching up there in the middle of the night, not finding a handhold and flipping backwards on his head or her head or something like that. Lynx rail, are they, I know they're in Australia, I've heard about them, but does anybody know if they're still active? Or Lynx rail still going good? Okay, great. I came across them a few years ago, so I included them here, but I just haven't heard much about them. But they're doing the same stuff with truck scan, looking for missing bolts, coupler securement, broken springs, wedge rise, etc. So you see we got a lot of vendors out there of this equipment, and again, I'm not here to favor anyone. I just want to give you a menu of what's available. And this is a big breakthrough called TreadView that Bina Vision told me a lot of people are really hot about. They really like this, the ability to scan the entire surface of the wheel, finding flats, spalls, checks, cracks, shattered rims, flanges, chunks of flanges missing, things like that. Also back-to-back measurement on the wheel. So it looks at the entire surface here, and they have algorithms to measure the size of a shell. We have a 1-inch standard. I guess it'd be 25 millimeter roughly. If it's greater in diameter than 25 mils, it has to be taken out of the fleet. And they have automated algorithms to assess the shelling of the wheel tread and get those wheels fixed. Now, acoustic and ultrasound or ultrasonic bearing detection. Some of this was pioneered in Australia with a group called Railbam. They're very integrated in the US. There's a number of Railbam installations. The purpose of these systems is to listen, quote unquote, to the bearing to detect incipient failure before we have a catastrophic burn-off. It came about years ago. Some of the old heads, I remember them telling me when they do an inbound inspection, they'd say, well, rookie, listen, you can hear a bad bearing crunching when it comes by. And sure enough, someone picked up on that, smarter than me, and developed what's called acoustic detection and listening devices. And they can detect the signature of a bearing that is crunching inside when the cones get spalled and things like that. Heat systems may not always find that. They were developed in the early 90s, but they had so many false positives that people backed away from this technology because stopping a train is an extremely expensive proposition, not to mention safety issues. And so until they could refine this down to eliminate the false positives, this technology kind of sat on the shelf. But now they've secured a lot of those problems, and they're moving forward. So better software and hardware has won the day. The two major systems are TADS by TCCI and Railbam in Australia by Vipac. And I want to bring up this other one I'll show you in a minute, the ultrasound idea. So we've got a dispersion of both Railbam and TADS acoustic detectors around the country. You know, I told you we had 6,000 hotbox detectors because there we're trying to catch a thing already on fire. But now we're just trying to listen to the bearing and say it may have a couple more weeks or days of life in it and get it scheduled to get to the depot for remediation. As I said, Vipac is one of the leaders in this technology. Here's one of their systems right here. And TAD's the TTCI system, quite similar, et cetera. I can't tell you which is better. I really don't know. I think they both do a good job on acoustics. Now, this idea really caught my attention, and some of you folks in the room, again, smarter than me on ultrasound and detection, might have some ideas on this, but this gentleman approached me a year or two ago, and he said, I come from not the railroad industry, but the mining industry, and he was a specialist in listening to bearings on conveyor belts, ball grinders, and he could detect incipient failures in bearings with ultrasound by listening to the bearing steel on steel. So he came up with an idea to listen to the railroad bearing, not through the air with acoustics, but by shooting an ultrasound up through the rail, through the wheel plate, into the bearing and axle, and listening that way. Now that makes a lot of sense to me, because again, as I said, acoustics have some problems with background noise and wind and other things. So I think it's a good idea, and he's done some field testing of it. His name is Gene Matson. He's patented the system. We've got two systems. He's put one on a short line and one on a Class 1 railroad now. And as I said, he uses a ultrasonic or ultrasound device to listen to that bearing as the wheel goes across. And he says ultrasound through steel is a much better transmission medium than air is to find these failures. He can also find brakes that are left on, sticking brakes and air hose leaks with the same sound system. He's picking up these things as well. So here's a graph. This shows the remaining bearing life. It's going along here for 20 years or 10 years, whatever, doing fine. As it starts to fail, you can detect with ultrasound an incipient failure where you have about 10% of the life remaining. Gives you plenty of time to schedule that bearing in for replacement or whatever. If you're using acoustics, that would be represented down here around the P5 point, audible noise, where you may only have less than 1% of the bearing life left. And if you're using heat source infrared, you're on the verge of failure right there. So that's, again, the efficacy of ultrasound gives you a lot longer lead time to detect incipient failure and get something done in a proactive sense rather than reacting to a crisis. Also, as I said, he has shown you can listen to the bearings, the air brakes or hand brakes left on, dragging brakes, and air leaks all create an acoustic signature through this detection device. The initial results in installation show high reliability of finding defects, because by the time you find it with infrared, as I said, it's often already too late. Another thing he showed me some data on, which I found intriguing, was he did some infrared thermography work, and he was observing trains, and his analysis shows that on a typical train, 60% of the brakes do 90% of the stopping. And he said usually around 5% of the cars do not apply at all. Okay? That's pretty astounding for a system that we inspect every day. We do initial terminal test of air brakes to have that kind of variability in our air brake system. And he did this with thermal imaging. And as he explained, the way that bearings fail is hot wheels. When a wheel heats up because a brake is dragging, the lithium-based greases start breaking down around 190 to 200 degrees, and that starts the failure mode. So the root cause of a lot of bearing failures is simply a brake left on, a handbrake left on, or a brake dragging, or a brake not releasing. And here's another example showing the thermal imaging. These were 3 wheels coming by one of his detectors that were around 10 miles from the latest hotbox detector. The hotbox detector did not pick up these wheels that had wheel heat over 230 degrees, which is way above the breakdown temperature for, these are Fahrenheit, I'm sorry. For you Celsius fans in the audience, do the conversion. But it's way above the breakdown of lithium-type organic greases. And we're not detecting these things. So a lot of good stuff there, I think, going on. So his system uses a section of isolated rail with a rubber isolator pad, he calls it, a ultrasound transducer, listening up straight through the rail, through the wheel to that bearing This shows an example. We also found a bogie going by making a loud noise. He wasn't sure what it was. They got the train stop, looked. It was a brake shoe left up in the truck casting that was rubbing on the edge of the wheel. Not that it was going to cause a failure, but that just shows you what ultrasound can pick up. So here's a basic layout of a system installed at a major U.S. railway. Here's the rubber pads. So you isolate the rail acoustically for a short section here, and as the wheels come across, you listen to that bearing. That's the whole idea. Now, the end almost. What do we do with all this data? Are you all tired? We've seen a lot, right? It's amazing. Billions of terabytes of data daily in Australia, the US, Canada are coming into these major data warehouses. And the question is, what do we do with it? And that's a real challenge. And again, that's a good reason we got all these good young people in the industry that can deal with all these terabytes of data and figure out what to do with it, because it's way over my head, believe me. The thing called IRT is what we use in North America. It's run by the AAR, and it collects all the data from all the Wayside detectors. It's accessible by the various AAR members to look at their equipment. Outsiders can't get in, allegedly. Oh, here's a fact. I got these out of order, I'm sorry, but just take one locomotive, for instance, that's being monitored, can produce 250 gigabytes per day, and for 3,000 locomotives in a fleet, that's 730 terabytes per day coming somewhere to a data warehouse. Huge numbers. It's like the stuff the Pentagon deals with, I think, okay? Big stuff that we, in our industry. Private companies collect this data, but they're not sharing it between wheel people and rail people, et cetera. Railroads need to learn how to use this big data, as it's now being coined. I think you probably heard the same term in Australia, big data, right? Sort of like our president. Have you heard about, we got a new president, by the way, Mr. Trump. Everything with him is huge. So we're talking about huge data. It's going to be a huge program. That's the way he talks. Maybe you've heard that. Just a little levity there. But no, in seriousness, big data is something we really got to tackle. And more importantly, is how to utilize this information, how to do data mining, and how to use AI techniques, artificial intelligence, to find the trends and predictive relationships within the mounds of this data. And what we're trying to do is, from these billions of terabytes, is finding the equivalent needle in a haystack. We're trying to find that one hit that's a positive hit, that's an accurate hit, that tells us to do something proactive with that vehicle or that rail or what have you. So it's a real challenge when you're being washed with billions of terabytes of data and you got to go down to that one 8-bit word that tells you where the problem is. And we need the good smart brains to figure that out, I think. So, to conclude this, we've made significant advances in the last 15 years. Many of these advances have come at small startup companies. Like I told you, I knew Benavision when it was 2 guys in a garage, basically. And now they just got bought by Trimble, and you know, it just shows you that's the natural evolution. Vipac and IQ here in Australia got bought by WebTech. That's sort of the natural evolution of a lot of these startups. They need capital infusion. They need management talent. They need marketing talent, so they get with a bigger player. And so this is where this industry is moving. But these guys like this Matson guy I told you about, a lot of those guys still around with evolving technologies that may be bought up someday. But that's sort of what kind of the natural progression here. We need further testing on some of these emerging technologies like machine vision, ultrasound, et cetera. We also need the support of regulatory authorities to back this, whether industry concerns or federal concerns that set the standards. We need their backing. I'll have a slide. Next slide, I'll tell you a little more about that. These devices obviously eliminate the subjectivity of human inspections and improve the day-to-day reliability. And importantly, the last line there, they change finders into fixers. Instead of having 50 people out there with flashlights going like this, wouldn't it be great to put those people in a shop fixing the defects we know need fixing? Okay, that's a much better use of labor than walking down a string of 400 wagons, you know, in a rail yard. The next is to increase the deployment of these devices. We have to justify this capital expenditure through relief from costly mandated human inspections. Again, I'm not that familiar in Australia with what you deal with federally, but we are saddled in the US and Canada with these mandated manual inspections. Why? Because labor organizations have a large political sway. They keep the regulator authority well positioned with papers and phone calls. And so any attempts to maybe reduce labor inspections is met with political opposition. But we really need the regulatory assistance here to move this technology forward, to prove that it's better than the human. It's safer. I mean, we get lots of injuries with inspectors out there on high rail trucks, under freight cars, getting legs cut off and things. It's not the safest world. And you can do this with detectors in a very safe environment and eliminate those risks. It's a win-win for everybody. But the regulators have got to start incentivizing railroads to say, okay, if you invest in brake view or tread view or ultrasound, instead of inspecting that train every 1,500 miles, we'll let you go 3,000 miles. That's a start, okay? And instead of inspecting that track twice a week in a high rail truck, you only have to inspect it once if you're using machine vision for sleeper inspection. Those are the kinds of economic incentives that I hear from our railroad clients that say, you know, if the regulatory guys would get off of our back, we'd buy more of this stuff because they know it works and they know it's good. As I said, I've said many times, moving from reactive maintenance to preventive maintenance. And as I said, our final challenge is what to do with all the big data. We need advances in data mining, data warehousing, especially looking at the trends in this data. As I told you, I gave you one idea of taking detector data on wedge rise, taking detector data on wheel profile, taking detector data on truck performance, merging it all together. We don't even get close to doing that now because all these databases are in silos. But they need to start looking at the interrelationships and the crosstalk between these detectors to really extract the maximum benefits from the system. We just can't have human beings sitting out there in rooms pouring through terabytes of data. It has to be automated, has to use artificial intelligence tools, etc. Now, I want to acknowledge a number of people that helped me with this paper. First, Ravi for facilitating this lecture, and multiple emails back and forth over the last 6 months, and a couple phone calls here and there. But Ravi's been great to work with to help get this thing organized. But I really thank all these people, the women and men on this list that I spent time with face-to-face or on the phone and doing research with, and provided me with a lot of the information I brought to you tonight. So a big thank you to all these folks. It wouldn't have been easy otherwise. And that's it, folks. Did we make our time? Are we close? Are we over? A little bit over. Thank you.